Hello, I'm Adam Kalai, and I'm here to tell you about efficient learning with arbitrary covariate shift. This is joint work with Varun Kanade from Oxford, and I'm at Microsoft Research. What is learning with arbitrary covariate shift? Well, it's a model of pack learning where we get rid of the assumption that the training examples and test examples are drawn from the same distribution and they now may be drawn from different distributions. And it's long been known that you can't really guarantee accuracy when the training examples and test examples are drawn from different distributions, arbitrary distributions, as long as, even if the training examples and test examples are labeled noiselessly by the same function, f star. So in this example here, you can see that clearly where we're trying to classify a half space, and the half space could be either of the two dashed lines. We don't know which one, so we just can't predict on the unlabeled test examples, which are shown as black circles. And this has long been known. In recent work, a model of PQ learning was introduced by Goldwasser, myself, my partner Yael Kalai, and Montesser, where in this model you have arbitrary training and test distributions of examples, but you get to abstain, and you have unlabeled test examples at training time. So that latter condition is sometimes called semi-supervised learning, where you have unlabeled test examples. And when you get to abstain, that's also called prediction with a rejection option, and knows what it knows algorithm, selective classifications, and many other names. It's been studied for a long time, but those combinations hadn't been studied until then. And they were able to get guarantees for arbitrary families of functions. Let's say a family of C of bounded VC dimension. Okay, and what they were able to show is that given these unlabeled test examples and labeled training examples, they could guarantee future errors on test examples at a rate of epsilon. Okay, so future examples drawn from the distribution Q, they would have an epsilon rate of both not abstaining, classifying them, and misclassifying them, classifying them incorrectly. So that's nice. Now you would like to guarantee a low abstinence rate on Q. You can't guarantee epsilon abstinence rate on Q. You can actually guarantee epsilon abstinence on future examples drawn from the training distribution because you've gotten training examples. And the nice thing is this is possible even though we don't know what the training and test distributions P and Q are. We just have unlabeled samples from the test distribution and labeled samples from the training distribution. And so this is the definition of PQ learning. You get almost no errors on test examples and almost no rejections on future examples drawn from the training distribution. What that says is actually that wherever the training and test overlap, you won't be rejecting. Or more formally, what this implies is a condition on the abstinence rate on test examples of at most the statistical distance between the distributions. And the statistical distance is also called the total variation distance. It's zero if the distributions are identical, and if they're totally disjoint, then it could be one. In any case, you're guaranteeing at most zero epsilon error rate on future test examples, and then the rate of abstaining is somewhere between, the bound is somewhere between 0 and 1. In the case where they're identical, you get pack-like bounds. In the case where they're disjoint, you get not very useful bounds. But it's kind of interesting because even to determine whether the distributions are identical or disjoint can't be done statistically in large spaces. So nonetheless, you can get these guarantees. Okay, so again, we're afraid of rejecting examples from the training distribution, and we're also afraid of getting errors on the test distribution. That's we need to avoid those two things. So now I want to argue that covariate shift is common. Some people say it's almost more common than not having it. So let's take a simple example of classifying lung scans as normal, healthy, or abnormal. And suppose our training data was collected prior to 2019 and was labeled by radiologists. And then the test examples were collected starting in 2019, where there's COVID. So clearly there's a new disease, a new type of abnormal lung scans that you may have never seen before. Let's see if our model applies. So are we using the same target function at train and test time? Yes, we're still trying to predict normal, healthy or unhealthy, those were unhealthy. The function itself didn't change. What did change is the data. Do we have unlabeled test examples? Are we in a semi-supervised model or a transductive model where we see in advance our unlabeled examples? No, unfortunately, this example doesn't quite fit because we don't have the unlabeled test examples. In many applications you do, but in many applications you don't. This is one where you don't. However, this is a good illustration because in retrospect, we could use it. So at the end of the week, let's say every week, we could go back and run the algorithm. At the end of the week, we have unlabeled test examples, and we can use those to reclassify our data. And then we would realize, gee, we want to retrack some of our predictions. Our classifier now abstains on a bunch of predictions. We had this whole group of weird new looking scans that as a group look different, a bit different than the scans we were familiar with. Maybe individually we wouldn't have spotted them, but as a group we now know that there's something fishy there and we might not classify in them. Okay, so this recent work, this old model of PQ learning, well, it's not old, but it's recent, is a model of PAC learning with covariate shift, arbitrary covariate shift, where you can abstain. And they show that they introduce an algorithm called the rejectron algorithm that shows that you can efficiently do PQ learning as long as you can find an efficient, what's called proper agnostic learner, which means that given an arbitrary noisy data set with arbitrary labels, you can find the best classifier in the class. And that's also called empirical risk minimization. It's a very well-studied problem, but it's often can be hard in practice. In this paper, what we do is we introduce a new algorithm that's a little simpler and a little more efficient in the sense that we reduce PQ learning to what's called reliable learning, which is a model of learning that's known to be a bit easier than agnostic learning. And we also show the converse, that reliable learning can be reduced to PQ learning, so they're equivalent. So we really understand the computational needs of PQ learning are at least equivalent to those of reliable learning. What is reliable learning? Well, I'll talk about it soon, but reliable learning basically means you want a model of learning where you're going to have no false positives or very few false positives, you guarantee, and subject to that, you get accuracy guarantees as high as possible. So, for example, the class of parity functions is a class of functions that are known to, well, we don't know noisy parity learning algorithms. We can't use the rejectron algorithm for them, but we do have a reliable algorithm for learning parities. So we can use slice and dice to learn parities, for example. So what is the algorithm? That's mainly what I'm going to talk about today. I'm going to talk about how to run the slice and dice algorithm. Well, what are the inputs to the slice and dice algorithm? The inputs are labeled training examples and unlabeled test examples, okay? And the first step of the algorithm is to find a classifier, to just run a standard machine learning algorithm, a standard PAC learning algorithm on the labeled training examples, ignoring the test examples, to find a separator that splits the data, okay? And that's really just a pre-processing step. The rest of the slice and dice algorithm is going to decide where we want to abstain. It's going to use this predictor to predict, but it's going to decide where to abstain. So in some sense, this can be combined with any kind of standard machine learning pipeline, where it's just kind of a post-processing step that's deciding where should we abstain. And what we're going to do is we're going to focus first, we're going to focus on the negative slice. So the first step is to slice the data, where we find the training and test examples which the predictor would have predicted are negative, let's say. Okay, and we call that the negative slice. And we can just do that by running our predictor on the examples. And then we're going to use what I call the reliable learner, which is guaranteed to have very few false positives. So we're going to create a fake data set where we're going to try to distinguish the training examples from the test examples, okay? So we'll call the training examples negative and the test examples positive. And the reliable learner is going to guarantee that it has very few false positives. So it's not going to call almost any of the training examples test examples. And this is known to be a bit easier than agnostic learning, or believed to be, I should say. So the algorithm finds some separator. In this case, it finds this horizontal separator here, which separates off quite a few of the test examples from the training examples. I could have separated off one more. And then we're going to just dice them. We're going to abstain on those. We're going to throw them out. We're not going to classify those examples. And then you might guess it, we're going to repeat. We're going to find another classifier. Here we can find this diagonal classifier that separates off a bunch of test examples reliably. It doesn't classify almost any of the training examples as tests there. And we're going to use that distinguisher to abstain again. And we're going to repeat until there's no way to reliably distinguish. And so one thing you can see here that might be kind of clear is if these things are really reliable, if they're not cutting off any training examples, we're going to meet our abstaining guarantee. We're not going to abstain on many examples from the training distribution because these classifiers are very reliable. They shouldn't classify any of the training or many of the training examples as test examples. Okay. What's less clear is that we're going to get error guarantees, but that does follow from our analysis. Once you can no longer find a reliable distinguisher, that's good enough to give accurate. You're in good shape to give accurate classifications. Your predictor C will be accurate. And you might guess it, that's what we're going to do in the second step as well. Now we're going to focus on the positive slice of examples at the classifier and see what if predicted as positive. And again, we're going to just try to distinguish the test examples from the training examples with this trick of creating a fake data set and running our reliable learner. And then putting it all together, the way our classifier works is we just output the predictions of C, except wherever we diced, wherever we removed the examples. And now you might be wondering, why do we need to slice in the first place? Why can't we just try to distinguish the test examples from the training examples? And that's a good question. So the obvious idea is to just try to do that. Well, here we can distinguish all these examples on the top. You don't need to slice. But we cannot distinguish this group on the bottom. You can see there's no way to draw a half space to separate out that clump of test examples. Plus, as we saw before, those could be positive or negative. We don't know. So we can't really guarantee accuracy and classify those examples. And yet there's no way to abstain on them by classifiers in the family. So that's really why you need to slice in the first place. This is also a good example to see why you need to see that group of unlabeled examples. Why you need unlabeled examples as input to the algorithm in the first place. Why can't you just abstain on funny-looking examples, which is what most prior work in this sort of abstaining model of machine learning does. The way it works is it sort of says, oh, this example looks really weird, like the examples on the top. But what it misses is a clump of new examples. So in the coronavirus example, there might be a scan. Any individual single coronavirus scan might actually look not that strange. Maybe it's like something, not that far off from things you've seen. And so you might classify it. But when you see a group of them with a pattern of difference, then you may say, okay, I'm not willing to confidently classify on this group. So in summary, in previous work, it was shown how to PQ learn with arbitrary covariate shift, as long as you can do what's called proper agnostic learning. Here we give a new algorithm that does it as long as you can do reliable learning. So it's a bit simpler algorithm as well. And we show the converse, that reliable learning can also be reduced to PQ learning. So they're equivalent in terms of their computational and data efficiency needs.